Hello and welcome. In today's video, we're going to be talking about I/O programming. Now, if you have no idea what I/O programming is, if you're curious, if maybe you've used Node.js, libevent, or something of the sort, and you're really curious how they work, then this video is for you. Also, if you just want to learn, then this video is also for you. So let's get started. Who this is for? There are no strong technical prerequisites, but you have to have some comfort with C programming language because we're going to be showing snippets. And so, as I said, if you already have used Node.js and you know that Node.js, for instance, is single-threaded, but it is event-driven. And so what does event-driven mean? How is it able to serve multiple connections at the same time despite being single-threaded? Right? Where does all of this performance come from? Then we're going to demystify that in this video, but this is more on a general level. It's not specific to Node.js, or it's more about how input-output progressed throughout the years. So if you're looking for some kind of a server from scratch tutorial, this is not it. This is more about concepts over code completeness, though it lays the foundation for you to build your own things, basically. How is this video structured? So we're going to go from first principles to modern primitive, meaning how things have evolved throughout the years, basically from like 1980s until modern I/O programming. That sounds like a lot, but not really, because such things kind of take time to develop, to mature. And so the idea is that each chapter solves the previous one's problem or challenges. And yeah, the fact that we can start from first principles kind of sets some easy basis, and then we can go incrementally higher in difficulty until we finally understand how modern input-output programming works. And the question on everyone's mind, why C? Why not Go? Why not Rust, Python, Node, etc.? Well, first of all, the kernel exposes its API in C, like read, write, EPOL, IOUring. If you don't know what these are, we're going to be talking about them. But the idea is that C maps one-to-one to system calls, so there is no hidden layer between you and the kernel. Go, Rust, Python, etc. They eventually all call this C function. There's also no garbage collector. There's no runtime, no green thread. So there is nothing that stands in the way of your program and the kernel. Like I said, you just have to have some comfort with C syntax, because I'll be explaining all these snippets, all the code that we're going to walk through. Yeah, the idea is that C is kind of the language of the kernel, so to speak. And there is no abstraction between your code and the system call. Now this is going to be a multi-part video, so it's going to be cut into separate videos. And in today's video, we're going to start with part one, the problem. So what is the problem that we're trying to solve? Why do we do I/O programming? What is this all about? So we're going to lay the foundation of what issue we're trying to solve. And then we're going to start optimizing things, and we're going to go crazy with the optimizations, but not in this video, further down the line. Now, I want you to take a moment and think about I/O, not I/O programming, like I/O in general. What is input-output, right? What is something that's considered I/O? So take a couple of seconds, pause the video, think about it, and then resume. All right. If you have thought about disks, sockets, pipes, terminals, etc., that's about right. That's like 99% of the cases. There are more, but yeah, these are common. Input, output, right? Reading something from a file, from outputting something to a terminal, reading like a key from a keyboard, etc. These are all input, output. And general rule of thumb is that everything that is outside your CPU and your process's RAM is input output. And the reason for that is your CPU has registers, right? And these are extremely fast to read and to write from. And then there is also the RAM, right? Where the CPU can read data from the RAM into the registers. It's also relatively fast. It's not as fast as registers, of course. And that's why you have like L1, L2 caches in between, etc. But these are kind of easily accessible to your CPU. Now, the CPU is extremely fast at, computing and moving data, etc. And so if it's moving from one register to another, it's incredibly fast. If it's moving from memory to register, it is, still, it's slower than registers, of course, the resistor to register, but it's still okay speed. And CPUs, of course, they optimize these things, such as, for example, when it's moving data, while the data is moving, it can run other things. So there are a lot of optimizations. But anything past this boundary, like, for example, a hard drive, now that is way slower. And so it has to read from the hard drive into, like the memory, and that is incredibly slower. And this is all, again, relative to the native speed of the CPU, right? So if you think about it from a human time, it is still like fast, but from a CPU perspective, that is slow. And so that's the idea. If you're sending like a packet over the internet, like this is, for example, I don't know, like Ethernet like device or whatever, right? You have like a cable and you're going to send it across the globe. In CPU times, that's like probably thousands of years relative to the CPU time. So that is input output, anything that is external to your kind of CPU and memory. So input output in your code. Now you've probably written some of these kind of lines. If you didn't, well, I'm going to explain them. So you have like read, write, receive, send. These are all kind of primitives to communicate. Now most of what I'm going to be talking about is going to be on the Unix family of operating systems. So we're going to be dealing a lot with file descriptors. We're going to explain what file descriptor is in a moment, but the idea here is that we're reading from like a keyboard, for example, the first instruction, and then we're writing something to a terminal, right? And then receiving data from like a network packet, etc. So it's kind of, these are all input output instructions. And now the next important thing we have to understand is the user space and the kernel space. Usually your code, like your program, is a bunch of instructions, right? These run in the user space, so the CPU is going to execute them one by one in user space. And then there are some special instructions like read. It will need to run in kernel space because you are not going to perform the read yourself, right? You don't have the implementation of the read as far as your program is concerned. It's just kind of an interface, right? It's more like a signature, right? The function that you call, and the actual implementation depends on the operating system, hence the kernel. And so kernel space in general has higher privileges. And this is important because, normal programs cannot access everything on the system, right? And the kernel or the operating system makes sure that certain programs can access or cannot access certain files, etc. So that is the main kind of separation. And then once the read finishes, your program goes back to it, or the CPU continues running your program in user space. And this is where we have to talk about the system call boundary. So in your program, or rather your program is running in user space at first. And this is where you have your program, your libc, built-in libraries, runtime, and then you're performing a read. And let's say you're reading, for example, from a network socket. And the moment the CPU is at the read instruction, it's going to traverse the syscall boundary, and now it's going to switch into kernel space. And in this kind of kernel space, this is where the syscall handler is, like the actual implementation of read is going to execute. And yeah, it's going to have to communicate with the hardware and then do what it needs to do. And then it's going to give you the data back in your buffer, and your code continues in user space. But this line, the boundary, is the important thing here. And note that the boundary, we cross it twice, right? Because we have to switch to kernel space, and then we have to switch back to user space. But you get the idea. I mentioned that read is just an interface, right? We don't really have to know how it works. We don't provide an implementation for it. And that's because at the end of the day, the operating system is an abstraction layer. It helps us deal with kind of low-level things that otherwise would be a pain to deal with, like creating files on the disk, right? It's handling all that low-level implementation. For example, the operating system talks with the drivers. It does really a lot of low-level things that makes it easy for us programmer to write more kind of higher level, think on a higher level abstraction layer. So we don't really have to think about what kind of bits to send to which address, which corresponds to the, Ethernet hardware, for example. No, you just write send and the operating system takes care for it. And one thing about abstraction layer, or abstraction layers in general, is that they are not free. And I don't mean free like as in free money, but they do have a cost associated with them. And that is unavoidable, right? Because when you're sending a packet, you do have to pay for that cost to do the transaction, so to speak. And whole problem of input-output programming is how to minimize this. We want to minimize this cost. So we're going to be talking mostly in the Unix universe, and that's because they have everything is a file. And that is the abstraction that the Unix operating system family use, is that kind of a file on the disk is a file, a socket is a file, a pipe is a file. And so you can think of these file, when I say file, generally like file descriptor or FD for short. And you can think of it as like a UID. You can think of it as like unique identifier for which kind of, which file, which socket, etc. And so what this allows us to do as programmers is that we have the same call, but we can address different things with the same API. And so we can write a buffer with size n to like a socket, to a file, to a pipe, another process, right, etc., etc. So it's the same API, it's just what this parameter FD corresponds to. All right, we already mentioned that abstractions aren't free, and that whenever we do a read or a write, we have syscalls. And system calls often have to switch context. Plus, there are memory copies, because we don't know how the operating system is handling memory. When I'm reading a buffer, am I getting it directly? Am I getting kind of a copy? There is a lot going on under the hood. So let's see the anatomy of a read instruction. So our code calls read with a file descriptor. And this, for example, again, could be like, let's say from a file, for instance, and then we're going to cross the boundary. And so here we have context switching. And then the kernel is going to look up the file descriptor. It has its own code algorithm for what does this file descriptor corresponds to, right? Because we have that abstraction that we can address many things with a file descriptor. The kernel has to figure out, what is this? Is it a file on a disk? Is it a socket, etc.? So it has to do its job and then communicate via the driver to fetch the data or, do what it needs to do, and then it needs to return. So what this context switching mean is that the CPU is executing your program, and then it needs to kind of, you have a function call to an operating system sort of routine, so to speak, the actual read. And it needs to run in a higher privileges, right? Because it's going to talk with the drivers, with hardware, etc. And so during this context switch, it's going to kind of back all the data corresponding to your runtime, like the instruction pointer, the register, right? It needs to pack the state of your program, save it, like push it in a stack or something, and then switch mode into kernel space, run in a higher privilege mode, and then it needs to roll back. So it needs to kind of pop all your program state kind of back into the right values and continue your program. So we have another context switching here. So in total, we have 2 mode switches. We have 1 buffer copy at least, because you're reading into a buffer, right? And whatever the driver is doing. So read may seem simple, but there is a lot going on under the hood. However, we can't really do anything without syscalls, right? Because a program or useful program needs to communicate with the outside world. So it's kind of like the door to a lot of things. And these are kind of most of the instructions that we can use. Read, write, open, already mentioned them. And as I explained, a file descriptor, you can think of it as like an integer handle. It's just an idea that we shouldn't mutate, obviously, but the kernel knows what it is. That's the idea. So let's talk about a small program that does read and write and analyze it. All right. So in this case, we have a main function that is opening a file, an actual file data.txt in read-only mode. We pre-allocate an array of 4 kilobytes. We call read and we print how many bytes came back, right? N here is how many bytes came back from the actual read, because the buffer needs to be, big enough. That's just the way how it is in C. And the crucial line in here is, of course, read, because anything after this will not be executed until we do the context switching, switch to kernel mode. The kernel does what it needs to do and then gives us the data in the buffer, right? So nothing after that line runs until the read returns. So the printf doesn't fire, no other IO happens, and basically while the system is working on our read, our thread is asleep or parked. And that's an important concept. So what blocking really means, it means that the thread goes to sleep and the scheduler, the operating system scheduler, can run other programs. Now, this is not necessarily a bad thing. If you have, for example, usually you have a lot of programs open on your CPU, and if one is sleeping, you do want other programs to run at the same time. So this is not necessarily a waste. But the problem is that if your program kind of is doing many things and not just one thing, then you're kind of blocked until the read continues or finishes before you can continue with your program. And so usually one read equals one nap. Well, how long the nap depends how how big the data is and what kind of file descriptor you're reading, etc. And yeah, this is kind of the timeline. The idea is that you have a read, and then your thread is going to be parked. And what's important here is that user thread is kind of so we're not really in a multi-threaded program, right? It's just a single main function, but a thread is kind of the smallest unit of execution from like an OS perspective that a CPU can execute, right? A CPU executes a thread. Now, of course, it runs instruction, but a thread is a bunch of instructions. So even though you have like a single main function, it still equals one thread, right? When you have more than one thread, then you're multi-threading. But it's just about the context here, about the vocabulary rather. And so one thread, one conversation. And what this means is if you sleep on a socket A, for example, you cannot serve socket B. So you can only do one thing at a time. Let's look at an example. If you have 2 clients and you have a single threaded program, and let's say client A connects to your program first, and client A is from the other side of the world, connection is really, really, really slow, and it's taking forever, and client P is trying to connect, he's just gonna be stuck waiting because you're still kind of blocked reading from A, and he's still sending the data stream or whatever, and so you have a really bad throughput. And the idea is now what can we do about this, right? How can we optimize this? And I already know the solution that you have in mind, and yes, it is completely valid. But first, let's look at the TCP server. Then we bind it together, so we tell the operating system, hey, this server has this address, etc. Listen. So now the server is in listen mode, and we accept, and this line is going to block until someone connects to the server. And when someone connects to the server, we're going to read what that client is sending. What does he want, right? And this is also blocking. It's going to block until the client sends the data. And the issue is, what if the client never sends anything, right? The program is just going to be stuck here forever. But yeah, this is the idea of a blocking TCP server, after which we just reply with hello world. So it's going to be HTTP version 1.1, so 200, so that's success, hello, and we're going to close the connections in the server. And the solution you've been thinking about was probably something like, make it more threaded, right? Add more threads. And that's a valid solution. For example, Apache used a fork for quite a while. If you're unfamiliar with fork, it's a C kind of system call again that kind of, you have a bunch of instructions, right? And when the CPU executes fork, it's going to create another process that is the same copy of your current program, except this returns like n, and based on n, you kind of know if you're on the main thread or on your cloned, if you're in the main process or on the cloned process. This is not a thread, it's a process. So you're creating a new process. That's what fork does. But processes are expensive, of course. You're copying literally everything. And so another solution is to use threads. And this is probably the solution you've been thinking about. Something like a serve client function that we, for example, can create via pthreads. And this would be the file descriptor of the client. It's way cheaper than fork because it's just a thread. Still shares the memory, right? So you have to be careful about it's here where you have to talk about mutexes and whatever. But for simplicity, we're not going to sort of dive deep into this. And this is how a threaded one thread per connection server would look like. So it's the same main, except now we're going to be infinitely listening, or rather infinitely accepting connections. And now because pthreads and C programming, right, the parameter passing is a little bit ugly. We need to pass like a void pointer, and we have to kind of allocate the integer or the file descriptor here. So we have to malloc it, and then we're going to block at accept. Once we accept passes, right? So we have a connection. We're just going to create a new thread, handle client with a client file descriptor, and then that's going to run a new thread, and our main thread is going back to the beginning and listens again. And this works. It's a perfectly valid solution, and has been working for quite a while. The problem is threads, they are cheaper, right? But they're not free again. So there is a memory cost associated with each thread, and the more connections you have, the more memory it's going to consume until eventually your system will run out of memory. So it's still a good solution if, for example, you know that you're not going to serve, huge amount of connections. So it works under some kind of known circumstances. However, there is another hidden tax, context switching, that every thread swap flashes registers, etc. And the idea here is that if you have, for example, a 4 cores CPU, and you have lots of threads, that are running. That's still not a lot, but let's suppose it is. What they're going to end up doing is that the CPU can only execute one thread at a time, right? And so they're just going to be competing over the available resources. And when the CPU switches from one thread to another, it needs to back up its state and then run another thread. And then backs up the state of that thread and then pops the other thread state, etc., etc. And so it's going to be doing more switching than actual working. Now, another solution to this, and now we're moving into the non-blocking aspect, is to refuse to sleep. And what this means is that if basically there is no data ready, I'm going to continue. I don't have to wait for it. And we can do that using FCNTL, which stands for file control. It is the Swiss Army knife syscall for tweaking file descriptor attributes. And the idea is, it's a syscall again. We're telling the operating system that, hey, for this file descriptor, I want to set the flag to non-blocking. So I don't want to be blocked whenever I'm doing, an operation on this file descriptor. There's also get flag if you want to sort of get what the current flags is. There is a lot of things you can do with this function. And so if we add this FCNTL to our code, what ends up happening is that the next time we're at read, we're actually not going to be blocked. It's going to return instantly. And how do we kind of know if the read is successful or not? There are two parameters that we have to check, or two values that we have to check. So the first value we have to check n, which is usually the size of the read. If it's positive, it means we have got n bytes in buffer, so the result is successful. So it did actually return the values, and we can proceed with our processing. If n is 0, the peer has closed the connection, so no data has been received basically. However, we have to also check error number. If the error number is E again, or E would block, it means that the data is not ready. So the operating system is fetching the data for us, and we have to come back later and check again. So here we can do some other work and then, for example, jump back to the read somewhere down the line. If it's none of these, then this is actually a real error, and we have to check the error number for other error codes. Some kind of critical issue happened, and we have to, check it. And this idea or this concept may actually lead to a misconception that if the data is ready, you can just keep looping. And this is not a great idea, because if you're reading, for instance, let's say this file descriptor comes from like a socket, network socket, and we're waiting for client data, and we're just reading and reading and reading, and the client simply hasn't sent any data, then basically we're wasting 100% of the CPU. So what's happening in this code is that if n is positive, we're going to break out of the loop, right? And then do whatever we want to do with the data. If not, and we have EA again, then we continue, which means we jump back into the while loop. And for the most part, this is going to be while true, read, while true, read. And so while true, you're doing context switching twice, right? Because this is still a system call. Yes, it does return directly, doesn't block, but you're still crossing the system boundary. You're still switching from user space to kernel space. And this is burning 100% of the CPU. And that's why sometimes having your thread put to sleep is not really a bad idea at the end of the day, right? You leave room for other things to be executed. That can be perfectly valid if you have nothing meaningful to do in your program. But we're talking in a case where you actually have meaningful things to do in your program. Like, for example, you rented a virtual private server, you're hosting your backend over there, and you want to serve multiple clients. So if you're waiting for one client, you still want to listen for more clients, and so you always have something meaningful to do. And then you definitely don't want to do this pattern. this burns. So your thread is not in sleep mode, right? It's not parked, but it's still kind of, now it's worse because it's not doing anything meaningful, just burning CPU. Now this marks the end of this video. In the next video, we're going to be talking about multiplexing or batching. So please look forward to that. If you made it this far, congratulations. I hope this has been informative. If you have any questions, post them in the comment. If you noticed any inconsistencies, if you have any remarks or corrections, also please let me know. Thank you for watching and see you in the next one. Have a good one.